The correct trig sub on this is A sine theta. Right? A sine theta. This right here is the form. The form we have here is a squared minus x squared. Right? So a is 1. So our trig sub should be a sine theta. X is replaced with 1 sine theta. I don't really need the 1. Right? And now I take the derivative. Dx is cosine theta d theta. And then the square root of 1 minus x squared turns into cosine theta. Rewrite the problem. The numerator is x squared. X is sine theta, so sine theta squared on top. The bottom is the square root part. The square root part is cosine theta. Times dx, which is cosine theta, d theta. Cosines cancel, reduce. Sine squared theta d theta. Power reduced, double angle. 1/2. 1 minus cosine 2 theta d theta.
How much credit do we get if we got there?
Well, more credit than if you didn't get there. Right? Okay, got to there, right? Now you can just take the antiderivative of each of these separately. The 1/2 can come out, right? So my next line will be, I now am taking the antiderivative. So this would be 1/2 equals 1/2. Now the antiderivative. Antiderivative of 1 is theta. And then I have minus the antiderivative of cosine of 2 theta is 1/2 sine 2 theta, right? You have to scale. You have to scale out the 2 plus c. And then I promised you this, didn't I? Didn't I promise you this? I promised you. I told you last week I wanted to give you a quiz today that had the cosine, that had a double angle in it. I think I said that. So I delivered today, right? So here we go. Minus, now this, use the double angle, right? So that becomes 2 sine theta, 2 cosine, 2 sine theta, cosine theta. The 1/2 and the 2 cancel, reduce. And you get just sine theta, cosine theta, plus c. And then you either make a triangle or maybe you have the information. But I'm going to keep going. The triangle, I base my triangle off of that information right there. That sine theta is x over 1. And sine is opposite over hypotenuse. And then that lets me solve for the adjacent side. And so I can fill everything else out here. So 1/2. Okay, theta, how do you get theta? Inverse sine on both sides there. So that's inverse sine of x. And then minus sine of theta, which is x over 1x, whatever. And then cosine theta, which is that over 1, which is this. That's it right there. Yes?
So this is like a stupid question, but why is it sine squared 1/3 cosine?
Wait, what?
Like the...
Oh, okay, yeah, got you. Well, I think you might be able to answer that yourself. Think about what you're asking. Why is it, right? Take the derivative. Times, right? Chain rule, right? So you'll have negative sign now. Yeah, unfortunately.
So was it okay if, because I think on my side I had one like negative 1/4 because it's distributed of 1/2, but then I had the 2 sine cosine theta. So it's like instead of canceling to the 1/2, I didn't like that part.
Yeah, I'll have to look. Yeah, I mean, yeah, don't ask me how much I'm going to take off for what you did. I need to look at them, right? Yes?
When you turn that cosine t theta into sine theta cosine, that's an identity, right?
That's an identity. Wait, the which one? The
After you derive it. So
antiderivative.
Yeah.
And we had the 1/2 sine 2 theta. Yes, that's an identity. That's the double angle identity. Well, maybe afterward. Yeah, after class. You can email, but just use paper next time. That way it's easier. Yeah, no, it's all right. Yeah. Okay, so my honest opinion of that is that that was like an easy quiz. That was an easy quiz. And I don't mean that in a bad way. I'm just being like, look, that was stuff we covered, what, more than a week ago, right? So, you know, that should be pretty solid. Now, you know, it was a pop quiz. You didn't know it was coming, whatever. But make sure that you understand the trig sub, because on your test, you're going to see it on your test. You're going to see it. You're going to need to know what trig sub to use. You're going to need, you know, what's going to happen. You could get a cosine squared, a sine squared. You could get a cosine cubed. You get secants and tangents, right? So anything could come. And before class, that's what I was doing. I was deciding what I was going to give you for the quiz.
That makes sense.
So I was looking at the solutions, and I was just scrolling along. Like I could have given you this one, something like this. But I was looking at what integral you wind up with, and I didn't want to do any secants and tangents. I wanted it to come out to be a certain way, and so I picked this one right here, and I just used 1 and 1 instead of 9 and 25. This is a homework problem. So you can see it turns out to a sine squared, which is, yeah. Anyway, okay. So today, we've eaten 20 minutes up. Today, well, let's look at our schedule. First of all, we are right on schedule for where we're supposed to be. We are the 21st. We are in partial fractions, right? And our exam is going to be right before spring break, so we still got a couple of weeks. And so that's going to be a big test right there. All right, so last time, if you don't remember, what we did last time is I went through and I said, let's look at all these like special types of integrals we could wind up with, and let's make sure we understand how to do each one of those. And now what we do is we get into this section, 6.3, rational functions, partial fractions. So when we talk about partial fractions, we are talking about how we find the antiderivative of rational functions. Rational functions from college algebra is anytime you take a polynomial and divide it by another polynomial. That's a rational function. And I have examples here of different rational functions. And I want to point out some things with these rational functions. The first one, f, you have a polynomial on top, polynomial on the bottom, right? What is the degree of the numerator? 3. What is the degree? When I say degree, what am I talking about? Highest power of x. So the degree of the numerator is 3. Degree of denominator? 1. Okay, so that'll be important in a minute. How about this second one? Degree of numerator? Degree of denominator? 3. Okay. This one, 4 and 3, right? 2 and 3, 2 and 2, right? But every one of these is a polynomial divided by a polynomial. If we had to do the integral of these right now, any of them, we would be in some pretty serious trouble. Like, we don't have anything that's going to make that go easily, because none of them look like any of the things we talked about last class. Remember, last class was very specific, right? Constant over linear repeated, linear over quadratic, irreducible, right? All these different things. None of these look like that at all, right? Do you all agree? None of those look like those real nice ones. So we need a strategy for integrating, finding the antiderivative of rational functions, and it is called partial fraction decomposition. That's the technique.
That's why he's supposed to look at the freaking yes.
That's why.
Okay.
Yeah. So if you don't recall partial fraction decomposition, I'm going to run through it really quick. I think when you're in college algebra and you learn it, you're at a different level than you are now. Like mathematically, maturity-wise, you're at a higher place now. So you should be able to absorb this a little faster. We'll see. But I'm not going to teach it. I'm not going to teach it like this is day one. You've never seen it. Okay. I'm going to assume you know a little bit about it. So these are my official notes for it, which I'm not going to go through my notes because they read like a math textbook. But I had to be very precise in my notes, and so That's the notes. I'm going to do it a different way. I'm just going to show you basically how we do it, all right? Just like scratch paper. So the way partial fractions works is this. Let's say that you have some expression on top, and on the bottom, let's say you have, what do I want to start with? Two factors, two things being multiplied, and each one of these are linear. A specific example of this. I'll give you a specific example underneath this. Okay? The idea here is that if you ever see this, then we should be able to rip this apart into two things being added together. So there's a way that somehow we can get two things that when we add them, we get back this. And what it's going to be, this first fraction will be A. A is some number, we don't know what it is yet, but that's some number over that first linear, let's call this linear 1 right here, and let's call this linear 2. This will be the first linear expression, and then we'll have some other number over the second linear expression. So we can decompose something into two pieces. Let me do it on this one. Let me change the top here from x to, let's make it 1 so it'll be a little easier to work with. So what we're saying is that this can somehow become this. Now, getting from here to here is kind of our question. How do we get from here to here? We need to know at this point that this can be done, but we'll talk about how that process works. But just, do you agree that if I could get from here to here, if I could go from here to here, do you agree that these two integrals, I could separate in two integrals and they would each be easy, relatively? Yes. Why are these easy?
Natural log.
These are natural logs. This is a constant over linear, so we should be able to handle that with a natural log. The problem for us is getting from here to here, and that's what partial fraction decomposition is, all right? Again, I'm not going to go through the method yet. I just want to show you like what we're setting up for. Okay, now the next thing says if you have, let's say you take this linear, let me change the problem a little bit. From here on out, I'm going to give you examples like this instead of like writing the word linear over and over. So what if you have this instead? What if you have, let's say 1 over, let's say I have a linear expression 1 plus x. Let's say this is cubed. And then here x minus 4, and then I'm going to make that one to the first power, and then let's say x plus 3, and let's say that's squared. Okay, the process of partial fractions says that we should somehow be able to rip that apart into pieces. Now the way it works is that you're going to have, these are all linear, right? That's linear. I'm just going to put ln, right? These are all linear expressions. They're different though, right? Each of these is different. This one is what we call repeated. Why do you think we call it repeated? Because it's cubed, right? And so is that one over there. Those are both repeated. This one's not repeated. So how do we handle linear expressions in the denominator that are repeated? Here's how. First thing we do is we write a over that first linear factor, okay? But we don't cube it, we just write the linear factor. Then we write b, which is some other number we don't know, over that linear factor, but now we write it squared. And then, what do you think? C over that linear, not yet, the first linear factor, but what? Cubed. It's like you build up the powers. So if you have a linear factor that's repeated, you start with a number over that linear factor, then a number over that linear factor squared, one number over that linear factor cubed, and you keep on building up until you get to the highest power. Yes?
Can it be 1, 2, 3, or can it be 3, 2?
You could go 3, 2, 1. Because there's addition, you could move it around.
And that's only for 1/3 of the entire problem.
Yeah, I still need this, right?
No.
So now what do I do for that? Well, that's linear, right? So I have another constant d over that linear factor. But that one's not repeated, see? So I only need to write it one time. And then the last linear factor, a, b, c, d, e, right? X plus 3, f, x plus 3 what? Quantity squared. And then I can be done. There is some way, I see you there. There is some way to go from here to here. There's some method that'll take me from here to here. If I can do it, then each of these are easy to do because constant over linear repeated, constant over linear repeated, constant over linear, constant over linear, constant over linear repeated are all things we talked about last class. Yes?
So is this like algebra?
Yeah, it's going to require algebra for us to do it.
Oh,
I haven't gone through, we're going to go through it. What I'm trying to get you to see is when you write this down, when you have your problem, you need to know what it decomposes into, and then you go after actually finding what A, B, C, D, E, and F are. Okay, but we need to know what this turns into. Yes?
How does it work that x plus 3 plus x plus 3 squared over, under E, under F, how does that turn into the problem?
Well, exactly. Somehow, if we put all this together, we can get to there. Right? Look, if I write this down,
Maybe just one example, like one example.
if I write that down, can you all add that together?
oh, you multiply by the.
You get a common denominator, right? So you would multiply here by x minus 4 over x minus 4. And then over here you'd multiply by x plus 1, x plus 1. Yeah, you're multiplying by the same, so you get a common denominator. Up here, when you multiply here to here, you get x minus 4. Then plus, now you multiply this times this, you get 2x plus 2. And that's all going to be over what? Your common denominator, which is x minus 4 times x plus 1. Right?
Yeah.
Now if I put this together, you get 3x minus 2 over the two linear factors.
And that little bit of algebra is called least common denominator.
Well, when you put these together, you're getting a common denominator. So look, what we're doing is not this, right? We're not starting with this problem and turning it into this. We are starting here and going that direction. So the point is that if you see two linear factors down here, you can ignore the top. If you see two linear factors down here, then what you should expect is that this should break apart to be some number over the first linear factor and then some other number over the other linear factor. Getting from here back to there is the hard part. Well, that's what partial fractions are. Let me keep going. We only have one more type of thing to worry about, and that is if we see something where we have on top something and on the bottom we have a quadratic that's irreducible. What does that mean? Can't be factored. I thought we did that already though. Didn't we? We did that already. But when we did it before, the quadratic that was irreducible on the bottom, the numerator was a number, or it was something else. In the problems that we're going to look at, it doesn't have to be a number. Like this right here, right? I'm not sure if that factors, who cares, but if that's a quadratic, let's say it was irreducible, notice the numerator's not a number. So you can't use the method we learned last class. You have to do something first. So I need to give you the idea here. If you have an irreducible quadratic here, then what we're going to try and do is turn that into something over that irreducible quadratic. The thing that goes on top is not a though. It's actually ax plus b. It's a linear expression, a generic linear expression. So if you back up, think about what we did just before this. If we see linear factors down here, we put a constant on top of them. If we see irreducible quadratic factors here, we put a linear on top. And why do you think we do this? Yeah, because then we can use the method that we learned already, which is Remember that technique that I showed you where you make something happen? Like you let u be the denominator and you try and massage the numerator into looking like the derivative. I told you it was the method I like to use, but we can handle that like that now. Like we could use that method on that. Let me give you another example. Let's say we had, I'm not going to put a 1 up there. Let's say we had something on the bottom, I mean on the top, and on the bottom, let's say we have x squared plus 4. That's an irreducible quadratic, isn't it? That's a quadratic that can't be factored. Let's say next to it, let's say I have that cubed. It's a repeated quadratic, irreducible. And then let's say next to it I have another irreducible quadratic like this. What that would turn into is, well, what do you think?
Linear on top.
Linear on top, ax plus b, and then what goes on the bottom? X squared plus 4, that's the irreducible quadratic, but it's repeated, right? So I'm going to have to do it 2 more times. So I'm going to have to go, what, cx plus d over x squared plus 4 squared, and then plus ex plus f over x squared plus 4 cubed. I'm not done. I got to do the other irreducible quadratic, ef g x h over x squared plus x plus 1. And that's not repeated, so that would be it. So for each, let me see if we can recap. For each linear factor in the bottom, we have to do a number over that linear factor. If the linear factor is repeated, then we have to do it several times till we build up to the power. And if the bottom is an irreducible quadratic, then we do the same process, but up top is linears instead of just letters, right? Just constants. This is what my notes say. Maybe it makes a little more sense now. I don't know. Look at that right there. Let's say that your denominator is a bunch of linear factors, right? Dot, dot, dot. I have n linear factors. Then if I have n linear factors, what I'm going to do is break it down to be a number over the first linear factor, a number over the second linear factor, and I keep doing that, right? The second note says, what if it's repeated? What if you have a repeated linear factor on the bottom? Linear, repeated. Then you have to build it up. First the linear, then the linear squared, linear cubed, and you build up to the power of k. And I just basically say the same thing for irreducible quadratics. I think we should do an example. Yes?
I was going to say, so it's acceptable too to just use subscripts instead of lines.
We like to use subscripts because with subscripts you are not restricted to the 26 letters, and you could theoretically have a polynomial that has, 100 terms in it, and then you run out of letters. So mathematicians prefer the subscripts because you can go forever with them. Yes?
Is this usually used in computer science?
What?
Subscripts?
Oh yeah, absolutely, because if you only have 26 letters to work with, then Okay, so let me get to the actual method, okay? Here's the strategy. We need an actual method to do this, all right? How do you get from one place to the other here? The first thing we're going to do is when we're looking at our problem, right, there's an integral we're looking at. We're going to inspect the degree of the numerator and denominator. We're going to look at the degrees. If the degree of the numerator, that's the one on top, if that degree is smaller than the degree on the bottom, then we're going to proceed to the next step. However, if the degree on the top is greater than or equal to the degree on the bottom, we have to first use long division.
That's fucking.
We have to do long division first. All right? And then what we do is, for whatever we have left, we're going to do these things where we break it down, decompose, and then we have to go find those letters and then crank out an answer. So we're going to start with this example, which is going to be an easier example to start, right? We look at that, and if you go through again our little Rolodex of techniques, there's nothing we can really use for this. I mean, maybe there's some weird thing we could do, but nothing seems natural. Like no basic U sub's not going to work here. Basic U sub's not going to work. Integration by parts, I don't know. Maybe you can get crazy with it and figure something out, but it's not a trig integral, right? Not cosine, sine, tangent, secant. Trig sub, do you see square root a squared minus x squared or something like that?
Back out an x from the top and then say it's square root.
You could do something maybe with the trig sub, but I think you're going to not like when you have to get, like, replace the x minus 1 with something. Yes?
With like that method thing, is it going to be kind of like the trig integrals where we have like kind of like a sheet like what's on the board?
You can only have what is online, and I don't have anything for partial fractions. So you need to know long division. You need to know, well, you need to know that long division is your first thing you look at, and then you also need to know how the breakdowns work. I think after we do a few examples, it's not as much to remember as you might be thinking it is. So I look at this right now. There's nothing I know how to do, but I do recognize that it's a rational function, a polynomial divided by a polynomial. So I look at the degree of the numerator, it's 3. I look at the degree of the denominator, it's 1. And then I have to remember, whenever that happens, I've got to start with long division. So that's where I'm going to go. So on the side here, I'm going to do long division. Everybody hates long division. Yeah. So I don't know why it drives people crazy so much. I really don't, but I know that it's a problem. So let me just remind you of something, and this is not to insult you. 15 divided by 4. All you do is you take 15, you divide by 4, we're back in elementary school, right? And then what do? You're saying, what do you multiply this by to get as close to this as possible without going over, right? So 3, you put it here, and then what do? 3 times this, and you put it under here, that's what, 12? And then you come through and you subtract, and then here you write 3, and then you play the same game over, right? Does 4 go into 3? No, so you'd be done here. This would be your remainder, wouldn't it? And when, yeah, we're not going to do decimals.
Back in my day, we just made them into decimals.
Yeah, I'm going further back. I'm going back to these days. Remainder 3, remember that? Okay, so you have 3 left over, yes? No? Okay. But this really means you have 3, and then this left over the divisor, 3 3/4. But this really means 3 plus 3/4. That's what 3 3/4 means. It means the number 3 plus 3/4. Mathematicians hate this notation. What is this notation called? Do y'all know? Mixed numbers. Mathematicians hate mixed numbers because it looks like multiplication, but it's not multiplication, and most people don't know it's actually addition. So, yeah, so anyway, this is what it is. Okay, so let me back up. If we do this, 15 divided by 4, what we do is we multiply by 3, we get our 12, we subtract. When we get to this step, if 4 doesn't go into that, our answer is going to be that number 3 plus whatever that remainder is over the divisor, which is 4. That's what we do back, way, way long ago. We're going to do the exact same thing, but with algebraic expressions. So what goes in the box? X cubed plus x, because it's in the numerator, right? Now when I write that, I write x cubed plus 0x squared plus x. Now I've put a 0x squared there to keep track of positions of things, because when I multiply things through, I might get an x squared to pop out, and I need a place to put it. Yes?
Long division and synthetic division is the same thing, right?
No. Long division works when you have any polynomial divided by any polynomial. Synthetic division only works when your denominator is a linear expression.
Which it is here, right?
It is here, so we could use synthetic, but synthetic is not always, the next problem, you can't use synthetic. So you follow me? If your denominator is linear, you could do synthetic. But if it's not, you have to use long. Yes?
Is synthetic division like part of whatever the new math, core math, core, there's new methods of doing math that are being taught.
Synthetic's been around for a long time. It's not one of those weird obscure things where they draw, you know, stars or whatever they're doing. It's not that. All right, everyone good? Now we play the game. We say, what do you multiply x by to get x cubed? X squared. You put it up here. It doesn't matter where you put it, right? X squared. Right? What do you multiply x by to get x cubed? You put x squared. Some people are like, line it up on the x squared. It doesn't matter. Just put it up top. Now we're going to do the same thing we did with the 4 times 3, right? We're going to multiply this times this. When you do that, you have to look at it like it distributes to each one. So what's x squared times x? X cubed. I put it underneath the x cubed. Check it out. X squared times negative 1? Negative x squared. I'm put it underneath the x squared. Negative x squared. Just like that.
You have to switch the sign.
Now, what did we do when we had that 12? We subtracted it, right? We're going to come through and we're going to change the signs. Everywhere we see a plus, make it minus. Everywhere we see a minus, make it plus. So now this becomes minus. This becomes plus. And now we add down, okay? These go away. This is x squared. And then here, this x comes down, and it's basically adding to nothing, so we get plus x. Now we try to see if we can do it again. Can you turn x into x squared? What do you multiply by? X. So I put plus x up here. Everyone good? And now we play that game again. We multiply that x, not the x squared. We already did that. This times these two. So x times x is x squared. Put it right here. X times negative 1 is negative x. And then they look like they're going to cancel, but they're not because I have to change the signs.
How do you change the signs again?
That's what we did back in the 12, 4, 15 divided by 4, remember?
No.
No? I just put on the board. Was it 4 outside?
Yeah.
4, we multiply by 3, you put 12 here, and then what do?
You subtract.
Subtract. That's exactly what we're doing.
Oh.
We're subtracting, right? We're changing the signs of what's there. Subtraction changes the signs. So cancel this. Here. Add 2x. Okay, play the game again. What do you multiply x by to turn it into 2x? 1. No, 2. X times 2 is 2x. And now we do it again. 2 times x is 2x. All right, 2 times negative 1 is negative 2. And then we come through again and we subtract, so it changes the signs. This becomes minus, this becomes plus. We add down, these go away. This becomes a 2. We stop when this can't be turned into this without using a fraction. So I can't turn x into 2, right? I mean, I actually could. I could multiply by 2 over x, couldn't I? But that's when we stop. We stop when when it requires a fraction from us. A fraction where x is in the denominator. Okay, so x, so that's it. This is our remainder, isn't it? It's our remainder. Okay, so here's what we're saying. Let's go back over here. We're saying that this integral just turns into this integral. It'll be the numerator, I mean not the numerator, it'll be that, what we just got, right?